Hey, so this lesson we're going to take a look at a different type of nuclear reaction. This one we're going to look at atoms where they fuse together, which is called nuclear fusion, plain and simply. So let's just jump into this and let's get started. Obviously fusion being the opposite of fission. Remember we had our fission reactions like alpha decay, beta decay, gamma decay. All right, so we had some vocabulary that we learned with that lesson, and we had different things that were happening. So let's just jump in and take a look. I'll go with black ink this time. Why not? So write a nuclear equation for the process of fusion for a protium atom and an alpha particle. Well, first and foremost, we need to know what a protium atom is. So protium is basically hydrogen 1. So there are various isotopes of hydrogen, and what you find on the periodic table is oftentimes referred to as protium. So we have a protium atom, so let's use our isotope notation, so that would be 1/1, correct? And then an alpha particle. So you should remember from the lessons with nuclear decay that alpha decay, we defined an alpha particle as a helium-4 atom. Like, remember in alpha decay, a helium-4 atom is emitted from the nucleus, that mass is lost, and we deducted that from the original nucleus that we started with to find out what our daughter product was. So we know what an alpha particle is. So I'm just going to add in an alpha particle, which I know is a helium-4 atom. And if you can't remember, we go back to our periodic table, and we see that helium has 2 protons. So that's why I knew to put a 2 on the bottom left side for our isotope notation. Okay. Let me zoom back out of that. Let's go back. So these are fusing together. So I'm going to draw my little arrow, and what we essentially have is fusing together. They come together and they collide. There's nothing here that suggests that there are any lost parts, so we just add across the top. 1 plus 4, that would be a total mass of 5. 1 plus 2, that would be a total of 3. And then we ask ourselves, do we use the 5 or do we use the 3 to figure out the new particle that is formed in this fusion process? And we know it's the bottom number because the bottom number tells us the atomic number in the notation, and the atomic number defines the atom itself. So we come over here and we find that atomic number 3 is lithium. All right, so now here on the periodic table you see 6.94 as the mass. That is the average mass. So there are isotopes of lithium, and so as we see from our problem here, we have an isotope of lithium. We would say that lithium-5. And of course this is a nuclear reaction, so there is a huge amount of energy that will be released in this. As those particles fuse together and then stay together, there is a huge amount of energy that is emitted as a result of that. All right, so it's pretty easy. So, but once again, you just have to do the math. Remember, the arrow in chemistry means yields, which is the same as to produce. You can loosely think of it as to make this, but yields means how much are you producing, how much is being made. Well, if we look across the top, 1 plus 4 is 5, check. And then 1 plus 2 equals 3, check. All particles are accounted for. All the mass, all the protons, there are no leftover parts, and so this right here is our balanced equation, nuclear equation for protium and an alpha particle fusing together. All right. Scroll down and do another one. All right. So, oh, I love that afternoon cup of coffee. I know I always say that in most of the videos. I can't help it. It's just delicious. Okay, let's write a nuclear equation for the process of 2 helium-3 atoms So 2 helium-3 nuclei. Nuclei is the plural form of nucleus, so that suggests, and it says 2, so that's why we have to say nuclei, undergoing fusion to yield a helium-4 atom. So here the dynamics are a little bit different. We're being told, excuse me, we're being told what's happening, so we don't have to guess as much. So helium-3 nuclei, all right? Helium-3 nuclei. So helium-3, and we're told we have 2 of them. So I'm just going to go ahead and write out 2 of them, and then we'll find that there's, we could write this some other way, but it still works out. So let's go back to our periodic table. We know helium, let's come back over here, still 2 protons. It's undergoing fusion and to yield a helium-4 atom. Well, we know a helium-4 atom, that's protium, right? So, I'm sorry, that's an alpha particle. So we're going to helium, 4, and 2. All right. So now we look at this, we realize that this is a nuclear reaction, so there's going to be a whole lot of energy released, so I'm just going to write energy. So now the question is there anything left over? Well, let's go across the top. We see we have how on the reactant side, we have 3 plus 3 across the top. That does not equal 4, so we've got some mass missing, because remember the top number represents our mass. So we need our mass to add up to a total of 6 on the right side, on the product side. On the bottom we have 2 protons here and 2 protons here. That's a total of 4 protons, but there's only 2 on this side, so we know we need 2 other protons on the other side. Okay? So we ask ourselves, question mark, what is it that's going to account for the 2 protons that are missing and add a mass of 2? Well, if we remember correctly, we know some isotope notation from the way we've been writing our elements, but we also know this. We also know an electron. We use an electron for 0 mass because it's so negligent that we just ignore it. So that would be the isotope notation for an electron. For a neutron and proton, what are the isotope notations? So neutrons do not change the atomic characteristic, or I should say they change the characteristics of mass, but they do not change the type of element that it is. So there can be multiple neutrons that are added or subtracted, and it will still be the same element. So the bottom number we know here is 0, but they do add mass of 1. A proton, it does change the atomic number, which is the bottom number, and it does, for every one of those, there is a mass of 1. So we have 3 isotope notations here to choose from. So we ask ourselves, what's left over? Well, if we were to come over here, if we were to put electrons here, well, that doesn't make any sense because this is a nuclear reaction, so it can't be that. All right? This is a nuclear reaction where we're looking at what's fusing together and we're looking at the nuclei left over. All right? Now, I'm not saying that there aren't electrons that fly around everywhere and are lost. That is most certainly the case. But right now we're basically looking at the overall effect. If we were to add neutrons, let's do that. Let's put a neutron up here. 4 plus 1 across the top is 5. Okay, we're almost there. Well, what happens if I add another one across the top? You would see that 1 plus 1 plus 4, that is 6. Well, that works. And on the bottom, we have 2 plus 2 is 4, and then we have 2 plus 0 is still 2. Well, that's how we know that the neutrons, those aren't it. So now we look at this, and there's only one other option left, and that is, looks like protons have to be it. Because if we do our math, we've got 3 plus 3 is 6, 4 plus 1 is 6, we're good. 2 plus 2 is 4 on the left side, the reactant side, and on the product side, 2 plus 1 is 3, plus another one is 4. We're good. So we found where the mass where the extra mass and the other particles were. And now, I'm going to erase all this stuff right here. And then that's our problem. Just obviously without the highlighted marks, I just highlighted that so you could see the parts. All right? So that whole thing there would represent the nuclear equation for this particular process. All right? Let's take a look at one more. All right? So our third example. We've got deuterium and tritium particles forming an alpha particle. So deuterium is hydrogen 2. Okay? Deuterium is hydrogen 2. It's just the name for it. And tritium, this is hydrogen 3. So you saw in a previous example, protium, that's hydrogen 1, deuterium is hydrogen 2, and tritium is hydrogen 3. These are just the names, common names for them. Hydrogen is still hydrogen, which is still an atomic number of 1 proton. So we're told that these nuclei come together and collide and form an alpha particle. And we know an alpha particle is a helium-4 atom. Okay? So a whole lot of energy is released, just automatically add that capital E. All right, we can already see from this problem here that on the bottom, 1 plus 1 on the reactant side is 2. And on the right side, we have 2 protons. So the number of protons on the bottom already adds up. So we can just go ahead and put a 0 right there on the bottom because 2 plus 0 is 2 on the right side and 1 plus 1 is 2 on the left side. On the right side, we've got 3 plus 2 is 5, which means we have to have 4 plus 1 on the product side. And there is only one particle that we're using at the moment that we know of that changes the mass by 1 but does not change the atomic number, and that is a neutron. Okay, so let me just move this over. There's our reaction. There's our nuclear reaction. It is balanced. Across the top, we've got on the products on the left side, the reactant side, 2 plus 3 is 5. On the right side, 4 plus 1 is 5. On the left side, the atomic number is 1 plus 1, that's 2. And on the right side, the atomic number is 2 plus 0, that is also 2. We're done. I encourage you to write these processes out yourself. Go back, take a look at this, look at the notes that I've given you, work on those practice problems, and check back in with me if you need some help. As always, stay curious, and I will see you in another video really soon. Bye.